Hello, here's a discussion about section 3.7, which is about implicit differentiation. I wanted to take a moment and talk about this idea of the word implicit. I want to remind you that implicit means something is implied as compared to explicit, which means something is directly said. So implied meaning something is understood to be true, but it's not said to be true. Our implication, our implied, is that we're going to say that when we see like x and y in an equation, and this is especially true for equations where I can't separate the y or isolate the y, that we're just going to imply that x is a differentiable function. Sorry, y is a differentiable function of x. That y isn't a variable. Y is a stand-in for a function of the other variable of x, right? And that leads to something that's very, very interesting, which is what happens when we take the derivative of y or some expression that uses y. In general, we are going to follow this plan. We're going to differentiate both sides. We are going to collect all the dy dx terms on one side and get everything else on the other side. We're going to factor out the dy dx, and then we'll solve for dy dx. Let's see this actually in action. Here we go. So here's our equation. And by the way, so when we do implicit differentiation, it's always going to be on an equation. So I am going to start by I feel like my pen is going. There we go. I'm going to differentiate both sides of this equation by x. So derivative of each side with respect to x. Now, one side is really, really easy. The derivative of 5x is just like the kinds of problems we've been doing all along, and that's simply 5. But let's focus in on this 3y squared for just a moment. Now, remember, y is not a variable. It is implied that y is a function. If that is the case, this requires the chain rule. Remember, we use the chain rule most often when we have a function inside of another function. We have a composite function. Here, the outside function is 3 in the x in the squared. The inside function is y. So if I take the derivative of this, I would take the derivative of the outside, which is 3 times 2, keep the inside the same, that's my y, reduce the power by 1, and then I follow it up with the derivative of y with respect to x. Well, that's dy dx. Let's try it again. Take the derivative of 2y. Derivative of 2y is 2 times the derivative of y, which is dy dx. So you can see the act of doing this creates these dy dx's. Step 2 is to get all the dy dx's on one side. It's already true for this one. Our next step is to factor out the dy dx's. So I'll pull that dy dx over to the side, and I get 3y plus 2 is equal to 5. And then if I solve for dy dx, I get dy dx must be 5 divided by 3y plus 2. All right, let's try that again. That was so much fun. All right, so I'm going to take the derivative with respect to x of both sides. And remember, wherever I see a y, I want to try to think about it as a composite function. So the derivative of 2y is 2 times the derivative of y, which is dy dx. Okay, derivative of x squared, 2x. No extra stuff on there because I'm taking the derivative of x. X is not a function of x, x is just x. Derivative of sine y. Again, this calls for a chain rule. derivative of the outside, leave the inside the same, multiplied by the derivative of the inside. Great, we've taken the derivative of both sides. Let's get all the dy dx's on the same side of the equal side. That means I'm going to subtract that cosine of y dy dx over to the other side. Let's factor out the dy dx. 2 minus cosine y is equal to 2x. And then let's divide by that 2 minus cosine y to isolate the dy dx. 2x over 2 minus cosine y. All right, looking pretty good. Great. All right, let's do this next problem, which gives, so it looks like we're given a very peculiar version of an equation of an ellipse. And we want to find a tangent line. Remember, for a tangent line, we need a slope and a point, right? Well, the point is already given to us, -1, 2. And let's see if we can find that slope. I'll take the derivative with respect to x of both sides of this equation. Right? Derivative of x squared with respect to x is 2x. Derivative of negative xy. Well, I'm going to remind you that it looks like these two things are being multiplied together. So it looks like we're probably going to use the product rule. I'm going to call the negative x first. I'm going to call the y the second. So when I say first, the negative x times the derivative of the second, which is dy dx, plus the second multiplied by the derivative of the first. The derivative of negative x is -1. And then we'll finish this. Oh, I'm sorry. Yep, that's good. And I'll finish this off with the derivative of y squared. Bring the power down, keep the inside the same, reduce the power by 1, and then don't forget about that chain rule, dy dx. On the other side of the equal sign, the derivative of 7 is 0. Let's clean this up a little bit. I've got 2x minus x dy dx minus y plus 2y dy dx. I will take everything that's not having a dy dx term over to the other side. And when I do that, I get negative x dy dx plus, this is equal to 0, plus 2y dy dx. I'll take that negative, that's 2x over to the other side, and I'll take that negative y over to the other side. Now I'll factor out that dy dx. And I'm just going to rewrite these. I don't like having that first term negative. If I can avoid it, I'll divide both sides by negative x minus 2y, negative x plus 2y, and I get that dy dx is equal to y minus 2x over 2y minus x. And there's our equation. Now, that is solving for that derivative. But remember, we're only doing this in service of trying to find the tangent line. Well, what's the slope then? The slope will be the value of this dy dx when we're at the point -1, 2. So every place I see an x, I'll put a -1, and every place I see a y, I'll put a 2. So 2 minus 2 times -1 over 2 times 2 minus a -1. See if I can clean that up a little bit. That looks like 2 plus 2 over 4 plus 1. That looks like 4/5. And quick look at that tangent line. Could that be 4/5? It could be. So let's say we think the tangent line is y equals y1, which is 2, plus the slope, 4/5 times x minus x1, which is -1, which is really x plus 1. Let's graph this. Let's see if we actually have something that makes sense. So I'm going to switch over to the calculator. All right, I'm going to start by creating a new document. Always like to do a new document. Let's go to the graphing, and I believe it was X. Oops, sorry. I'm going to do a little trick here. I'm going to go menu, and under graph edit entry, I'm just basically would say we're going to graph a relationship. We're not going to graph something that's in the form of y equals x, some function of x. And when we do that, we can simply type in the equation. I think it actually started out, is it x squared or y squared? I forget. X squared minus xy plus y squared. Okay. X squared minus, tricky part, x, explicitly say times y plus y squared is equal to 7. If I hit, and there's that. Does that look like the graph that was in the notes? Sure does. Excellent. Now, let's put in our tangent line. We can still be in relation mode. We're just going to have to put in the equal sign. What was our tangent? 2 plus 4/5. 2 plus control division, 4/5 to get that fraction, times the quantity x minus, I think it was x plus 1. Let's take a look. Yep, that sure does look like a tangent line at that point. Great. Go back to the notes. It also asks for the normal line. And remember, normal lines are perpendicular to tangent lines. Should really use a colon here, not a equal sign. So come on. Normal is going to be y equals 2, because you're still going to the same point. So it can be x plus 1. The difference is that the slope is the negative reciprocal. So let's put that in and double check our work. Hit the tab button, and again, y, the equal sign is right next to the trig button, and that was 2 minus control division for the fraction, 4 or 5/4, and then times, it was x, I think, plus 1. Hit enter, and indeed, those two lines look like they cross at a right angle, and they do look like they're tapping at that point 1, -2, or -1, 2. All right, great. So I think we did a great job on that one. Oh, more difficult problem. This isn't asking for the first derivative, it's asking for the second derivative. Let's go through the procedure to deal with that. And that is, we're going to find the first derivative, and then we're going to take the derivative of the derivative. So let's start by saying, let's take the derivative with respect to x of 2x cubed minus 3y squared is equal to the derivative of 8. Right? This is going to be 6x squared. And again, no extra chain rule because it's x. And this is going to be minus 6y times dy dx. Again, treat this y like it is the interior function of a composite function. The chain rule is the derivative of that y. And all this is equal to 0. I'm thinking 6x squared is equal to 6y dy dx. Therefore, dy dx is equal to 6x squared over 6y. Conclusion, dy dx is equal to x squared over y. Now, I want to find the second derivative. So what do? I'm going to take the derivative with respect to x of both sides of that equation. Now, when I take the derivative of y with respect to x, again, I get d squared y over dx squared. Again, we would simply just call that the second derivative of y with respect to x. On the other side, it looks like I've got a quotient rule. So I better have my quotient rule mantra ready to go. Bottom times the derivative of the top minus the top times the derivative of the bottom. And then this is all over the bottom squared. Let's clean that up just a little bit. 2xy minus x squared dy dx over y squared. This is not the official answer because the College Board does not like leaving dy dx as part of the answer. But luckily, we know what dy dx is. Calculated it. Oh, I guess I don't have it written clearly. dy dx is equal to x squared over y. So I can get my better answer for this second derivative of y with respect to x by saying 2xy minus x squared times x squared over y all over y squared. Now, the College Board will accept this answer if it was a written response, but in general, in multiple choice questions, it would never leave this form, which was I would describe as a fraction within a fraction. Easiest way to get rid of a fraction within a fraction is to multiply both numerator and denominator by that denominator in the upper part. So if I distribute this y across, I get 2xy squared. And when I do this across, the y's will cancel, leaving me just x to the fourth. And on the bottom, I'll have y cubed. And there's my answer to what is the second derivative for that curve. Right? Now, here's something I hate to confess. In the homework prior to this section, you have been doing problems like y is equal to x to the 1/2, and you're taking the derivative of that. Bring the power down, reduce the power by 1, 1 over 2 square root of x, something like that. Officially, we've never proved it. We have proved the derivative of x to the nth when n was positive integer. We also proved it when n was a negative integer, but we've never proved it when n was a fraction, just some rational expression. Well, we can now do this proof that this derivative is equal to n x to the n minus 1, regardless whether it's positive, negative, or a fraction. We can now prove it because we have this new tool called implicit differentiation. Here's how the proof goes. Let's say y is equal to x to the nth, and again, n is some fraction in the form p over q. P and q are integers. Right? In fact, I'll just rewrite it that way. Y is x to the p over q. All right? Let me take this expression. Drag one more time. I'll put this over here. All right. All right, so let's say we have that. Well, one thing that I could do for this expression is I could take each side of this expression to the qth power. And now what do I get? I get y to the q is equal to x to the p. Now I do that because p and q, as that are integers, I can now use the power rule on both sides of this equation. Take the derivative with respect to x of y to the qth power. That's not a 9, so I'm going to put a little tail on my q's. And the derivative with respect to x of x to the p power. This becomes q y to the q minus 1 on this side, and then the chain rule gives us an extra dy dx. This side ends up being p times x to the p minus 1. And there's no chain rule because we did it with, this is with respect to x. Let me solve for dy dx now. I get dy dx is equal to p over q, x to the p minus 1 on top, y to the q minus 1 on the bottom. And you might notice that this is p over q times this other expression. And this makes us, oops, q minus 1. This makes us happy. That's a terrible happy face. Try that again. That makes us happy because this p minus q, or p over q, we said already is equal to n. So I'm going to make that last change. This is already n times x to the p minus 1 over q, not q, y to the q minus 1. Great. But remember, our goal is to show that it's equal to n times x to the n minus 1. We're certainly not there yet. So let's do some other things. For example, y, our very first step, our very initial thing is to say that y is p over q, or x to the p over q. Oh, stop that. Go back. There we go. So let's do that change. N times x to the p minus 1 over y, not y. We're going to replace y with what y is equal to, which is x to the p over q. And then this is to the power of q minus 1. Okay, let's try to clean up that bottom. I get n times x to the p minus 1 over x to the p times q minus 1 over q. Well, that's a mess. See if we can unnecessify it. All right, I've got a fraction. The terms in the fraction have the same bases. So what I can do is I can try to solve this by subtracting those two exponents. And here's what it looks like. X to the power of p minus 1 minus p q minus 1 over q. You're like, this is not nicer. Okay. Well, I'll tell you what. Let's see if we can make it a little bit nicer. We have this big exponent, which is made up of two things, one of them a fraction. Let's use a common denominator. The common denominator is q. So now I've got, let's write out everything. Everything. And that is n x to the p minus 1 times q over q minus p times q minus 1 over q. Holy moly, do we have enough space to do this? N to the x. Let's take all of that numerator stuff and put it over one common denominator, which is q, and that is pq minus q minus pq minus, plus p. And again, all of that is all of that exponent is over q. All right, now switch pen colors because this pq and that pq cancel, leaving us n times x to the p minus q over q. And the q's are looking like 9s. Or in that case, an a. Stop that. All right? Oh, one more step. N x to the p over q minus q over q, which is 1. Do you see it now? N x p over q, I think we define p over q as n. So therefore, this is nx to the n minus 1. And there we have it. Holy moly, that was hard. All right. Hope you enjoyed that.